Okay, today we want to finish our discussion about diffusion models, so we may have a bit more material to talk about. Previous session, we see that noise conditional score networks are great options, but they have a missing point. The missing point is that at the end of the noise addition process, you are not the pure Gaussian noise. So we think of something different. The different things was built based on hierarchical Markovian hierarchical VAEs. We talk about these topics. Let me see. Yeah, you have this parts. I think we stop here. Maybe. Okay, we see that we have a forward diffusion process starting with x0, which is your observed data, and in a Markovian process, you add noise to your data until you reach a point called xt, and you can have the noise addition kernel is a Gaussian kernel, and also based on this Markovian relation, you can find a distribution of any of these latent variables given your observed data using the definition of this alpha bar. Okay. So we are at this point. We know that we have this whole of this several latent variables, and there was 3 restrictions. Let me write those restrictions. There were 3 restrictions from Markovian hierarchical VAE to BDM. The first one was let me write it as equal dimension between observation is x0 and latents, that we call them xi for I equal from 1 to t. This is the first restriction. This restriction was very important in terms of changing our formulation. The second one is that the encoder is linear Gaussian, and the last one is that the last latent is pure standard Gaussian. These are 3 differences between VDM and Markovian hierarchical VAE, and you see that how we can derive the distribution for xt given x0 here. Yes, this is the distribution over xt given x0 based on the fact that you know what is the kernel for consequence for neighboring latent variables. This was our notation update. Obviously, I have a problem here. I write q phi here, which was not correct, and now I update it. And the most important point is that the encoder part is has parameter free. You do not have any parameter for your encoder. Okay, and also we see that how we can guarantee the last latent is Gaussian if your alpha t bar is equals approximately to 0, then you guarantee that the final latent variable is pure Gaussian. So this is important to to satisfy the third condition here. And this is the joint. Now we want to talk about some definitions. The first one is the forward diffusion process. The forward diffusion process is the process that you follow to generate the latents given the observed data, the red arrows. And the reverse diffusion process is the process that you want to generate data. And it is simple in terms of diffusion. Why? Because you need a starting point, okay? You need a starting point to generate data. And you can, based on the three property, you can see that restriction, that starting point. What is that starting point here? What? Yeah, the last one is the standard Gaussian. Independent of your observed data, it is a standard Gaussian, okay? So you can sample from standard Gaussian and follow the blue arrows to generate data from your true data distribution. So this is important. This third property is very important to have your generative model. Okay, but what are these blue arrows? We know that the red arrows are Gaussian kernels. Yeah.
The training is to, I don't know, understand best red arrows, right?
The training is to reverse the red arrows.
So my question is that we fix the distribution and also the parameters.
We fix the encoder.
Yeah.
Yeah, the encoder is fixed.
So what is the learnable parameter?
This part. We want to talk about the learnable part now. Yeah. Yes?
Encoder part can alpha ever be 1 or is it always?
No, between 0 and 1, and it cannot be near 0. Because I want to talk about why it cannot be near 0. The very important point is that we do not know anything about the blue arrows yet. We do not know what is the kernel for the blue curve, okay? But this slide, you see what is the blue curve. For Gaussian forward diffusion, it means that if you're adding noise, kernel is Gaussian. And alpha t, this sign means it is less than 1, but it is almost near to 1, okay? For a Gaussian process with these types of alpha t, then you can claim and you can prove that the reverse diffusion is also Gaussian. This is the point. This is the most important point. It means that if you are adding a bit of noise, a little noise to your data, then you can claim that the inverse is also Gaussian. Does it make sense? It means that if your noise addition is very severe, then you cannot claim that you can recover your previous signal using a Gaussian again. But we have the reference, you can find the reference here, and it proved that if the forward process is Gaussian and alpha t is almost equal to 1, but lower or smaller, then the inverse is also a Gaussian curve. So p theta of xt minus 1, given xt is again a Gaussian process. So your task, this is not dot, this is colon, this is a comma, sorry. Your task is to find just these two, this vector and this matrix. So if the forward process is Gaussian, alpha t is almost 1, then the inverse can be Gaussian, and you can give the freedom to it so that you can train it based on data. But we know that this form is valid because the forward is Gaussian with alpha almost equal to 1. So the problem of training a BDM is equivalent to designing a model based on deep neural networks to produce these two parameters. The first one is the vector. The second one is a matrix. But we see that the second one is not important. Yes.
So columns change. X0 would also be the Gaussian. Yeah?
X0.
When they are back propagating.
No, the xt is Gaussian. But you apply some kernels over that Gaussian.
It stays Gaussian.
No, if this type of relation, if you have, for example, affine transformation here, then you can claim that let me try. previously, remember that we talked about Q sigma. Q sigma was something like this, because one of them was Gaussian, the other one was Gaussian, but the mean and covariance was non-linearly dependent on that Gaussian. Okay, exactly like this. And we claim that this is not Gaussian anymore. This is exactly the same. Do you remember?
Like, can you go to the previous slide that this chain?
Yeah.
Here.
This is Gaussian.
X is Gaussian, and then we are back propagating through the blue.
This is a kernel, Gaussian kernel. This blue curve, okay?
And the resulting distribution for xt minus 1 is still Gaussian.
No.
So what?
This is the problem, yeah.
So what does that p xt minus 1 given xt is Gaussian mean?
No. Pay attention to the fact that I want to. You cannot see. Sorry. Pay attention to the fact that how you are related, how the mean and covariance. I think it's better. Sorry. Can you see this line? No. You can see it. Okay. Then the point is that a p of xt is normal with 0 and also p of xt minus 1 given xt is a Gaussian kernel, but if here you have an affine transformation, affine of xt for the mean, then you can claim that p of xt minus 1 is Gaussian. But here it is a highly nonlinear neural network. Mu theta of xt and sigma theta of xt. Does it make sense why it is not Gaussian anymore?
And so p of xt minus 1 is the multiplication of these two terms, like p of xt times the p of xt minus 1.
You should integrate it out. Yeah. You should integrate out xt.
And the resulting is like
Is not Gaussian, yeah. But if this was an affine transformation and this was fixed, then you can claim that that was also Gaussian. Yeah. Any question? Okay, so because the forward have those two properties, we have the reverse as a Gaussian. No, now pay attention to the fact that there is some bottleneck here. We need alpha t to be equal almost to 0. Why?
normal distribution for x.
Yes, because of the third. If this happened, it means that the last one is coming from the standard Gaussian. First, we need alpha t to be less than 1 but near to 1 for all t. Why? Because of the reverse process. If this happened, the reverse process is also Gaussian. If it is not happening, you cannot have any claim over the reverse process. Okay? This is exactly the previous slide here. So we have two properties, and they should be satisfied together. What happened? Alpha t, the multiplication of alpha t should be equal to 0, but they cannot be near 0. They should be near 1. You have multiplication of these alpha 1, alpha 2, alpha 3 until alpha t. First, each of them is almost less or equal to 1, means 0.99. Also, we want this multiplication to be almost 0. What happened? You should increase t. You should increase t so that they are almost near 1, and also their multiplication is also 0. You should have large t. This is the problem with diffusion models. You should have large steps of sampling, because t represents how many processes should you follow to sample one data from your distribution. When, for example, typical number is 3,000, very large number. Okay? Does it make sense why t should be large? Any question? This is a very important point. Okay, so altogether you need t to be large. So what is the forward diffusion process? We know that forward diffusion process is a fixed add noise addition to the data using a Gaussian kernel. So for the first, I have this sample from the data set. I form this distribution, very easy, and then sample from that distribution. This is my x1. I continue this procedure for several times, and at the end, it is guaranteed that this data is coming from the true standard Gaussian distribution, from the pure standard Gaussian distribution. Why? Because I select T large, and this multiplication is equal to 0. This is just a simplification. We know that with 7 steps, we cannot achieve both of these properties. We know that. This is just for the representation. So this is the forward process, and the reverse process which you use during the training and also during the sampling is that you sample one data from here, because you know that the last one is the standard Gaussian. And then you have a kernel. This kernel is the reverse process. And we know that it is Gaussian because you select alpha almost equal to 1. Otherwise, you cannot claim it, okay? So you claim that it is this one. If we have a trained model, we will talk about how we can train it. If you have a trained model, you have a neural network that can provide you both of these two, this vector and this matrix, and as a result, you have this distribution. If you sample from this distribution, you can generate your X6 and continue this process. Yes.
So the way, so let's say like the model is training on the cat and dog images, right? And then how do I
on what images?
Cat and dog. Cat and dogs.
Cat and dogs. Okay.
Yeah. So in the sampling process, how do I only generate like sample from like a dog distribution?
You mean the conditioning?
Yes.
Yeah.
Well, because right now it's like purely random, right? You see a cat and dog.
Yeah, you know, this is on the things that we are talking about is the unconditional version. But it is very easy to show that how this diffusion model can be guided using one classifier. It means that you need just one classifier between cat and dog, any classifier. And that classifier can guide you through this process so that you can only generate dog images, not cat images. But unfortunately, we do not have time to talk about the conditional version. But we have two types of diffusion model, conditional diffusion with guided classifier and classifier free. Both of them can work in your scenario. But the basic is what we talk about here. Okay, so you continue, and you know that your neural network can accept a timestamp, and based on that timestamp, generate the mean and covariance matrix. It means that this is aware how many noise is added to your data. You have the timestamp, okay? And you continue this procedure. At the end, you have a sample from your data. So we know that this is just a visualization. It is not a dog anymore. It is based on the sample you generated from the standard Gaussian distribution. So at the end, you have sample from true data distribution. This is what happened in the diffusion model. Now we want to see how we train, because based on this figure, you can easily generate samples from them if you have these two models. So how we can train it? If you have this mu and sigma neural networks, then you can generate samples. This is our final topic in this course. How we can train this mu and sigma. And that's the learning. Okay?
What kind of model you use for mu?
Generally, because the sigma is not trained, this is not the problem. You see that how you can make it offline. But for this part, you generally use unit-based architecture because the input and output are of the same dimension. And there are some types of unit that can also accept the timestamp. Those type of unit are the best option for the diffusion models. Unit, input, output, similar, and they accept the timestamp. Exactly matched to your application.
Shouldn't we use recurrent models?
Recurrent?
So instead of just passing x1,
you want to pass all other latents?
Yeah.
That's because we have this type of connections. we can claim that we have this framework. If you have other connections, means if they are not Markovian, you cannot also use these things we talk about. Because all of things is based on the Markovian, step 1 Markovian property. If it is not, you cannot use each of those properties. Yeah. That's very simplification. You see that how it factorizes the distributions based on the first order Markovian property. Okay, yes?
Why do we need the timestamp? Because the X is also changing between two consecutive samples. So why the timestamp is needed?
Yes, you know, because X is input, but the information of the noise added to the data is not present in the X. It is a better guide for your model to understand the timestamp itself. Similar to noise conditions score networks. There we also add a sigma value input. Yeah, because the model want to tune its denoiser so that based on the input noise level, it denoise the data. It makes the problem much harder if you do not input this information to the model.
So why we do not add like the last mean or last sigma instead of timestamp? What does timestamp has to do?
Timestamp means how noisy. You know, you have a denoiser. This denoiser is tunable. This shows that how noise is added to the input. It can understand which part of the model should be activated. You have a model. They share property with each other because they can, based on just changing this timestamp, it changes its states, okay? From, for example, denoising a highly noisy data to a low noise data with a low level of noise. Because of this parameter sharing, their training becomes faster. If you want to train one denoiser for each step, you may have some problems and needs lots of data. But here they share their architecture. And just using this information, they change it so that it match the input. This is a property that you need. Good. So now we want to learn it, okay? We need the first thing we need is a conditioning trick, okay? We know that during the encoding process, data of xt is coming from this distribution. So, assume this encoder distribution, we know that this is Gaussian. But I claim that this distribution is equal to this one. Is it clear for all of you why they are similar? They are equal? Because of the Markov property, yeah. Because of the Markov property, you can easily add any x with index lower than t-1 to the conditioning part. So this is the conditioning trick, and we know that we have this property. But on the other hand, I can reformulate this distribution using the Bayes rule. The Bayes rule says that this conditional distribution is the condition of joint, is the distribution of the joint, or the distribution of condition. Just the Bayes rule. And I use the chain rule to factorize this distribution. If I factorize it using this procedure, I can, let's say, these two terms cancel each other, and we have this step. Okay? So the conditioning trick first, and then Bayes rule and chain rule together, I reach this point. We will see that how I can use it. So now we want to train VDM. One approach to train VDM or any latent variable, any latent based model is ELBO, similar to VAE. So I can find focus on one data point x0, one of the training samples. I want to change the decoder part, those mu theta and sigma theta, so that it gives higher probability to your data point x0. I know that this is not accessible because you cannot integrate out all the latent. As a replacement, we use the ELBO of x0 and theta, and we know that ELBO is a value that can be calculated easily. So I want to maximize the ELBO, so I should formulate ELBO for this problem. The ELBO states that the lower bound to the evidence can be calculated using this formulation. Assume that x1 to t is the latent, and this is the joint distribution of what you observe and all the latent, and the denominator is exactly your sampling distribution. This is the definition of ELBO, nothing more. Based on restriction number 3, I take out the x theta from the denominator. Why? Because I know that that distribution is known, and also it is not dependent on the model parameters. Why? P of x theta. What is the P of x theta? Xt, x uppercase T. The last one is always a standard Gaussian. You need it for generation. Okay. So I take out this part. Why I use this multiplication sign? Because we know previously that because of the Markov property, this joint can be factorized as this multiplication, and also for the denominator. We have previously shown these two properties. Okay. We know that P of xt is not dependent on theta, so it is P of xt. It is not P theta of xt, in contrast to BAE general case. Okay. The next part, I take out the t equal 1 from this multiplication, this one. Okay. Just pay attention to the fact that I talked about in these equalities, then you can review them again. They may be a bit ambiguous here. Okay. Just pay attention to the part that I talked about. From here to here, I take out the element here with t equals to 1. So it is starting from t equals to 2, and this is the term for t equals to 1. And also, the first term in this multiplication is also take out here, and this is the rest. What happened next? The logarithm is applied. The logarithm of all these is the logarithm of the multiplication is the log of each of them separately. Assume that these 3 are one part, these 2 are another part, so this is the logarithm of the first part plus the logarithm of the second part. Okay. And pay attention to the expectation. Expectation is fixed till now. What happened next? Based on slide number 32, which is our trick, what happened here? Pay attention to from this part to this part, we apply another thing. Q of xt, the condition on xt minus 1, based on our trick, we know that equals Q of xt, condition on xt minus 1 and x0. This is another change here, okay? So 2 changes. One, the logarithm of the multiplication is the logarithm of the first time plus the logarithm of the second, and also I replace Q of xt, condition on xt minus 1 with this. This is our trick, and now I want to replace this term. We previously derived a relation for this term, okay? I just applied that one. This is what happened from the previous slide to here, and now I just put away what happened here. This term is exactly previous one, but here, okay? Here you have multiplication of lots of terms. Do anyone have any marker?
No.
Can you give it to me? Here is a bit maybe confusing, but I want to talk about it. Thank you very much. Here we have multiplication of those terms inside the logarithm, okay? P theta of, I am writing exactly this term, just put it above. P theta of xt minus 1, condition on xt, the denominator of the denominator come to the denominator, so we have Q of xt minus 1, condition on x0, over Q q of xt minus 1 condition on xt and x0, condition on xt and x0 times q xt condition on x0. So pay attention to the fact that there are t minus 1 of these terms for different values of t. Let's talk about the first and second, okay? I put t equals to do in this term, okay? It's equals p theta of x, 2 minus 1 x1 times x2, q of x, 2 minus 1 x1 times x0, or q of x, 2 minus 1 x1, condition on x2 and x0, times q of x, let's say x2 given x0. I think it's okay. Now the next one. What happened in the next one? The next one is p theta of it's 3, x2 given x3 times q of x 3 minus 1 2 times x0 above over x3 minus x2 x3 x0 q of x3 x0. Two terms must cancel each other. Yeah, these two terms. Okay, two terms cancel, and this propagate through all the multiplications. You can check it, okay? And at the end, you have just there are at the first and at the end, you have two terms that cannot cancel each other. Those terms are here, okay? So where is the origin of this term? After this multiplication, two terms cannot cancel each other, the first and the last. These are those terms. And I put it away from the logarithm. So the logarithm of multiplication becomes the logarithm of the first times the logarithm of the second. And this is the remaining parts here. Okay? What happened from here to here is what I talked about in this equality. Now, what happened next? The next part is just, then you can see here that I can cancel this term with this term because they are logarithm. I can write it as logarithm of the multiplication. The multiplication, this term cancel this term. Okay, so this is the result. Make sense? Just review the point I talked about when you review the course. You can easily follow these equalities. And also for the second, when we have the logarithm of multiplication, we have the summation of the logarithm, nothing else. So we are at this point, and this is almost our final point. Now, what happened? I just shared this expectation over all parts. The first part, also I put away this, let me check, x0. No. I put away this term from the logarithm, so I have the logarithm of p theta of x0 given x1 plus the logarithm of pxt over xt over qxt given x0, just this one. So I have the expectation over the encoding of the log of p theta of x0 given x1. This is the first term. The expectation over exactly the same thing of this logarithm of these ratios, and also this summation. The summation and expectation change because they are both linear. So how you have the summation of the expectation of this logarithm. Clear? Okay. Now, if you have an expectation over something, the random variable which are not inside this term can be integrated out. Make sense? You have an expectation over, for example, here over x2. x2 is not here, so you can easily integrate out x2. So x2 is, let me write it, x2. Just pay attention to this relation. It can be applied to both three terms, okay? we have expectation over Q of x1 to t given x0 of, for example, the first one, log of p theta of x0 and x0 condition on x1. What is this integral? We know that the integral can be written as the integral over the distribution of the distribution 1 to t given x0 times the log of p theta of x0 given x1. D, everything which is here, dx1 to t. This is exactly the definition of the expectation. So, but pay attention to the fact that x0 and x1 is here, x0 is also here, but x2 till xt they just happened here. So what happened? I can write it as this one. The distribution, the integral. Again, I put the integral for those parts inside this Q. X2 till t of x0 d, the difference of those variables, x2 till xt, and the remaining part is here. It means that x1 and x0. What happened here? You have the integral of a distribution over the random vectors, so they integrated out. So what happened? As a result, I can write the expectation over x1 till xt given x0 of this term as expectation over just q of x1 given x0 of this term. This is what's remaining here. It means that just the random variables here are important in this distribution. The other random variable will be integrated out. So this is the change from this term to here. The second term is also just a function of xt and x0. So again, you have just the q of xt and x0 of this. So x1 to xt minus 1 will be clear. And the last one is also interesting. Here you have function of xt minus 1, xt and x0. So just you preserve them, and the other ones will be integrated out based on this idea. And this is almost the end of ELBO reformulation. So the ELBO around the point can be calculated by the summation of three terms. Term 1, term 2, term 3. Term 1 is very intuitive. What is term 1? It means that sample, I think I have, yeah. I will talk about. Let's talk about term 1. Pay attention to term 1. You want to calculate the expectation of log of p theta of x0 given x1 over this distribution. What happened? For calculating this expectation, what do? We sample from this distribution, use Monte Carlo estimation. This is our approach for almost all expectation. What is the sample from this distribution? If you have this data, sampling from that distribution is forming the kernel and sampling from the kernel, something like that. This is what you need to calculate the expectation using Monte Carlo estimation. You put it on this term. This is one sample. The noisy dog is a sample from this distribution. You put it here. So we want to calculate this expectation. We know that one estimation to it is using Monte Carlo estimation with only one sample. It means that this expectation equals the logarithm of p theta of x0 given x1, and x1 is the noisy dog. Okay. It means that assume that x0 is this dog. You need one sample from this distribution for Monte Carlo estimation, and that sample is the noisy dog. Then, based on the first term, what does the first term say? The first term says that a good model is a model that when you maximize the model distribution over D, given the x1 equal to this 4, it outputs your true data. What is this term intended to do? It is intended to reconstruct your data at the last part. So the first term is called the reconstruction term. Again, pay attention to this formulation. It means that give noisy data to your model. We know that this should be maximized because this ELBO, this is a part of ELBO, so it should be maximized. It says that give me a sample from your noisy data. A good model will give higher probability to the true data for that input. This is very intuitive. It means that a good model must be capable of reconstructing your data, giving the first noisy data, the first noisy latent. So we call it the reconstruction term. Okay?
So
yes.
V is the picture, yeah?
Because I do not want to use X anymore, I use V here, yeah. Okay? Yeah, as a result, this will be the best V for the maximization, which is the original sample. The second term, prior matching. The second term is this one, okay? I just apply a minus term, a minus here, and change the numerator and denominator of the logarithm. What is this expectation? Yes, it's a KL. It's a KL between these two distributions. The KL between Q of xt given x0 and P of xt. What does it say? It says that the model output for the last latent must be near to what you expect. What do you expect for P of xt? Pure noise. It is a prior matching. It matches your encoder at the end with what you expect. You expect to be pure noise. This also matches the last latent given what you observe with the pure noise. We will see that because the encoder is not trained, so what is Q of xt given x0? How we design the encoder? We design the encoder so that this distribution becomes a normal distribution over xt with mean 0 and covariance I. Okay? We design it so that this happens. And also, we use P of xt again to be normal over xt and 0 and I. So, what is the value of this KL? 0. By design, we satisfy this step. By our design of the forward diffusion process, we do something so that this KL becomes 0.
It wasn't even 0, it doesn't matter in terms of ELBO because it's independent of theta. So if you're optimizing over theta, that's just
you know, if you want to do the way that this is not Gaussian, then you need to add some parameter here so that you can optimize this term too. Otherwise, you have a term in your optimization which cannot be controlled and which may be large. Okay, but for simplification, first, exactly similar to VAE. In VAE, we can have the prior to be parametric, but we generally use a standard Gaussian. Here is the same. You do your encoding so that the last one is always Gaussian, and this term is always 0. Otherwise, if the last one is not Gaussian, you have a term here, and this term, you design your decoder so that it can cancel the encoder. But they mismatch. At the end, something is going, for example, to another distribution other than Gaussian, standard Gaussian. Then you start from a standard Gaussian. It means that there is a intrinsic mismatch between these two methods. So either you should parameterize your P theta of xt, you should parameterize this one, or use the fixed encoder so that the last one is standard Gaussian. Any question? Okay. We know that this is the conditional distribution of the encoder. This is what you use during your sampling process, and this is a prior matching term. The prior matching is very simple. If you have this one in the input, then the distribution over the last one is this kernel, and you know that alpha bar t is equal to 0. So as a result, we are certain that the last distribution is standard Gaussian. So we do not have a mismatch. So you can omit the second term because it is always 0. Pay attention to the fact that there are some cases and you can also train that part, but we do not talk about those topics, okay? But this is what happened in the original paper. This is exactly what happened in the original paper. Okay. So here I just talk about the fact that this term is not parametric. This term is not parametric, so how we can control it? The point is that this term is always 0, so you do not need to control it. It is controlled previously. Now we want to focus on the third term. The third term is the largest because it's a summation of several expectations. We know that the third term is expectation over this distribution of this logarithm. If you use chain rule, in this distribution, in this Q distribution, we know that this distribution can be factorized as this one using chain rule. Then put inside the expectation with respect to this one. What is this one? What is this expectation? Pay attention to the fact that this one is exactly here. What is it?
ELBO.
What?
ELBO.
This is KL. This is a KL. You know, you have a distribution, but it is in denominator, so you can add a minus term. Put it it is in the denominator. You can add a minus term. You have the KL between these two distributions, but previously you have an expectation over that. So this is the final formulation for the last term. Okay, the expectation of these two terms. We have an intuitive result why this should be true. Exactly here. What happened? This term says that if you want to maximize ELBO, you need to minimize this KL, the minus term, okay? What are these two distributions? We want to focus on these two distributions, okay? First, first about this, we want to talk about this distribution. We know that this distribution, p theta of xt minus 1 is given xt, is what exactly you need during your generation. It means that your model must be capable to have some information about the previous latent or the latent which is nearer to your true data distribution given xt. It means that it should give you a high probability to samples like this, given the condition like this. A good model is something like, a good model must have this property. What is so this is a denoising operator. You agree with me? This is denoising because we come from this point to another point which has lower level of the noise. So this is denoising based on model distribution, what you want to learn. The other distribution, Q of xt minus 1, given x0 and xt. First, pay attention to the fact that Q of xt given xt minus 1 is very clear for us. Why? Because it is the kernel. This is the kernel. But here you have something different. The index here is smaller than this index. So pay attention to here. It means that what?
So it's somehow forcing the learner the model to have decoder the same as the index.
To reverse the encoder, yeah, exactly. Well, we want to reach that point, exactly. This distribution said that assume you have access to the main data, to the training data that you select x0, and also a noisy version xt. How you can have information about the previous level? A previous level is a level which has lower noise. So it is again a denoising operator. Does it make sense why it is also a denoising? Because you have access to the true data, you have access to the noisy data, and you want to have an estimation or a distribution over this one. Does it make sense how it denoise? It is denoising this term, this image, this level of latent. So we call the third term the denoising matching. Why? Because you match, because you want to minimize the KL between these two distributions, and they are both denoisers. So you want to match the denoiser based on the model with the denoiser based on the encoder. The encoder itself has a denoiser. Okay, makes sense? Yes.
So the below one is Gaussian, as we.
This one?
Yes.
Yeah, it is correct.
So the upper one should also be Gaussian.
Yes, we prove that the upper one is also Gaussian. Now the point is that we talked in, exactly with your friend. Yes.
Can you come back to the previous slide?
Here?
Just, no, the previous one that
ELBO.
Slide
33. This one?
Maybe mine is different, but
I have uploaded a new version before the class.
okay, never mind. So we have three terms.
Yes.
First time you mentioned is the reconstruction term,
Yes.
and the third term is the denoising matching.
Yeah, these are the terms.
So I have a just question about the intuition. So the third term is pushing the model to have the reverse of the encoder the same as the
Yes.
encoder.
Yes.
But even that's why we need term one.
Yes.
If we force the reverse of the encoder be the same as the decoder, so we don't need the term one and just here's it.
Yes. But pay attention to this index. It is not working on the first one. It is just working on the second to the end. And also you are exactly, your point is exactly valid. We will merge these two terms now and change this index from 2 to 1. Yeah, exactly. You know, it is very intuitive. The loss of diffusion is very intuitive. The second term is not important because you match, but the first term match these two distributions. Coming from the original data to the first level, you can reverse it. Also, the second term is responsible for these others. From here to the end, term 3. From here, term 1. They are responsible to reverse the encoding. The intuition is exactly this. Now we will merge them together and you have just one loss. But because of the intuition because the reconstruction is the most important part, because that's what you finally observe as your generated data. So generally we separate it. But now I will show that it can be added to this term with this formulation. Okay. Here. So we have two distributions, and now if we minimize the KL between these two denoisers, it means that we are maximizing ELBO. We are making a model a better model. Okay? So this is another. Now I want to work on term 3, the point that we talked about. We know that the value of t in term 3 starts from 2. Exactly this, the intuition from this part. Let's consider this term for t equal to 1. I want to consider the term 3 for t equal to 1. I know that this t is not in my summation, but pay attention to what happened. If I put t equal to 1, I have the KL between this q and this p. What is this q? Q of x0 given x0, what happened? You have the distribution over a random variable, but the random variable is given, so it is not probabilistic anymore. It is a certain value. We generally replace it with a delta function, delta of x minus x0, but do not worry. I just have I need the intuition, not the formulation. Q of xt minus 1 given xt and x0, this distribution x0 is not probabilistic anymore because you are given x0. x0 is given to you, so that's a number. Here, a number or a vector or an image, a certain image, okay? And we can show that the KL between these two distributions equals minus the logarithm of the p theta of x0 given x1. So what happened? Do you follow this? What happened is that the first term, which is this one, expectation of this one, is exactly the third term for the index equal number 1. So, previously we showed that ELBO is this one. The first term was reconstruction, prior matching, denoiser matching. This term was 0 because we matched them together based on our encoding design. And we show that this logarithm is minus the KL for t equal to 1. So if I define r hat of x and theta, I have this formulation. The index changes from 2 to 1. I omit this term because it is 0. And also I merge this one and change the index from 1. Everything is clear? So we have a term that make a chain between these latents. How? The above is the encoder you design, the below is your model that make the chain. It is intended to reverse the process. Because of this, we call it reverse diffusion. The above one is the forward diffusion, the below is the reverse diffusion. So it is intended to reverse the forward diffusion process. And an important point, this one r hat x and theta and ELBO are equal optimization objective with respect to theta. Why? Because this is 0, and we show that this term can be designed, that can be considered as this term with t equal to 1. So it is not important whether to minimize this one, to maximize this one or maximize this one. Both of them result in a similar theta parameter or model parameter. Okay? Any question? So matching different denoisers, okay? I just to visually focus on how denoising is working, okay? The first distribution, I think the second distribution, yeah, no, the first. The first distribution in the denoiser matching is this, this process, is this distribution. We want to have something, we want to know something about xt minus 1, given we know that what was the original data that we add the noise, and also what is the noisier version. We want to reverse only the last step. We want to only reverse the last step. So it is one type of denoising. The other type is your model. But your model is not given x0. If it was given x0, everything was ideal. But your model is just given the xt. And want just based on xt reverse the process. It is a very hard process. You know, your encoder has access to x0, but your decoder, which is your model, does not access to x0. And this is the problem. Now we want to formulate. So we are matching two denoisers, so it is called denoiser matching. And the problem is that what is this distribution? Why? Because we want our model to make its distance lower and lower with this distribution. If we do not have a closed form solution or closed form distribution for the Q, then we have lots of problems. But there is a very interesting point, and that's we have, we know that q of xt given xt minus 1 is this one, q of xt given x0 is this one. You previously proved them. And we also, based on the Bayes rule, we have this distribution and kernel tree and our trick. So we know that the distribution we are intended to find has relation something like this. But you know that this one is Gaussian, this one is also Gaussian, and this one is also Gaussian. All of them are Gaussians. You have the ratio of 3 different Gaussians, the multiplication of 2 of them in the denominator and divided by another Gaussian. Each of these 3 can be replaced using these 2 kernels, okay? By working on this ratio, which is in your homework number 4, you can show that the distribution over xt minus 1, your encoder distribution over xt minus 1 given xt and x0 equals a Gaussian distribution. This is a game changer point. That the distribution you are looking for to make your model nearer and nearer is itself is a Gaussian distribution. And with parameter mu and covariance sigma q. The mean can be calculated as this one. You know that you have access to xt and x0, so you can easily calculate the mean, and alpha are defined at the design of your encoder. And also the covariance matrix equals this diagonal 4, where the sigma q to the power of 2 of t equals to this formulation. Again, you have access to all of them, so you can have the distribution. It means that if you design the encoder, then you can find the distribution for this xt minus 1, q of xt minus 1 given xt and x0. So we relax everything. We want our model to mimic the behavior of this distribution. If you have a model that can output exactly this distribution, always you have a perfect model, and you can inverse the forward diffusion easily. And the problem is that it's hard to mimic the behavior of this model. Okay? Yes?
Can we go back to the... Yes, so what the second term on the denominator, q xt minus 1 given x0, that the last...
Yeah?
Yeah, the right expression, after the equality.
Yeah?
Yes.
Okay.
In the denominator, the second, the right term. Yeah. So what is this function?
This is Gaussian for any t. You know? It means that...
Oh, for any t.
For any t. It means that just replace t minus 1 here. Okay? Any question? So, if you want to design your model to reverse the diffusion process, you need a model that can mimic this distribution. It means that output exactly its mean and it's exactly its covariance matrix. And we have the both of them. So, modeling the inverse diffusion, now you want to design this model to be exactly this distribution. Pay attention, both of them are Gaussian. So there is some intuition because the KL divergence between two Gaussian has a closed form. You may previously seen the closed form of the KL for two Gaussians. And that's this one. We know that the KL between two Gaussian can be formulated in a closed form solution like this. Now, pay attention to the one point. What happened if the covariance matrix of the distribution is equal? Here, I have a neural network that outputs a covariance matrix, but the covariance matrix for this distribution is independent of xt, x0. It is very evident. Based on the design of the encoder, you can give the covariance for any of these distributions. Yes? If you design the encoder, you can calculate q sigma to the power of 2 of t for any t. You agree? So, to relax my problem, I put this covariance matrix exactly equal to that numbers. Does it make sense? I am designing the decoder. I am designing my model. And I know that what this model should mimic has a covariance matrix which is independent of X. So I put my covariance, my model covariance, exactly equal to that number that I know. Make sense? And then I can relax this KL. If for two Gaussians the covariance is equal, you can relax the KL. So what happened for the forward denoiser? I know that the covariance is this one. Exactly, I use the same value for my model. So I want to compare two distributions, two Gaussian distributions. Why the covariance is similar, is equal? What happened to the formulation? This one and this one. So in my model, I just have access to xt, and I want to output this value, which is hard, because this value has access to x0 too, but I do not have access to x0. I am in the decoder part. I start from a standard Gaussian, and I want to reach that point. But the Gaussian, the covariance matrix of both of them is exactly similar. Why? Because I know that this covariance matrix is independent of these x values, and I select exactly similar value for my model. This was the point that I talked about before. We do not need to design the model for the covariance matrix. We fix the covariance matrix of our model. So based on slide number 84, you can show that the KL divergence between two distributions, which are both of them Gaussian with equal covariance matrix, is this value, but we know that they are equal. So I can replace them with sigma q, all of them are the same index. And as a result, so what happened here? We have this is exactly coming from the KL for Gaussians, okay? Now, this is the logarithm of 1, which is 0, d itself, the trace of identity matrix. The trace of an identity matrix is d, because they are of dimension d. These two terms cancel each other, just this term is remaining. And we know that the transpose time the vector is the L2 norm to the power of 2. So what happened? You do not need to design a covariance matrix, just design your model so that it can mimic the mean value of the encoder distribution we calculate. This is the idea. Instead of those complex, because if you want to design the covariance matrix, it's very complex because it has some properties, positive definiteness, something like that. You do not need to worry about the covariance matrix. Just design your mean value so that it can exactly mimic the behavior of the Q distribution. Okay, and we know that this scaling is this value because it is defined by design. If you design the encoder, you have defined it. Very easy, okay? So we have, this is just a recap of what we had before. We have the K divergence equal to this one. So we want to minimize, we want to design a model because this value is defined, I think, yeah, we have it here. This value, the sigma, the mu q is defined. Why? Because we know that the distribution of q over xt minus 1 given xt and x0, what is the formulation, and we find the mean, and you will find it in your homework, exactly this value. On the other hand, now you want a model that mimics this behavior in the mean, okay? And your model have access to xt. Your model you want to design has access to this xt. How do you design it? Pay attention to the fact that these numbers are given to you. Just the missing point is x0. How do you design it? If you are intended to design. Because you have xt for your model, because your model has access to xt, it is given. x0 is not given, okay? You design your mean of your model exactly similar to that formulation. you'd use xt exactly similar to what you intend to mimic. It is the trivial answer. You have access to xt, so trivially mimic the behavior in the new MOOC queue. So we exactly mimic that behavior, but we have some estimations here. Because you do not have access to x0, you must estimate it based on your inputs. Your inputs are xt, the noisier version, and t. What is the index? Does it make sense what happened here? Yes.
Why don't you have X0 on training?
Even on training, you want to you have the x0 start to add noise to it, and then you want to denoise it so that the last denoise version is as near as possible to x0. So you use x0 during the training as a reference. If you have access to it, because it is not what happened in practice. In practice, you just have the sample from the standard Gaussian distribution, and you should be able to generate samples based on just sample from the standard Gaussian. Yeah, you have it during training as a reference to make your ELBO maximize.
Also, we should always have it as a reference, not use it in our.
Yes. We have as a reference to for reconstruction. So this is what happened in the encoder. You need to mimic this behavior, and you have access to xt. So you design your model so that it exactly output the part related to xt, and you want to design and estimate this part, which is x0. So using this option in the above formulation, you can again simplify the KL. The KL is now become the distance between x hat theta and x0. Just replacement is enough. This is not enough. So you have a scaled version of this difference, and now we know that there is a summation over this KL in term 3. I just applied that summation, t equal to 1 to t of the expectation of this term. This term is exactly what happened above. So we have an expectation, but we have a summation. What should we do with the summation? Let's think of this expectation. I assume that t is coming from a uniform distribution over 1, 2 till t, uppercase t. If I reformulate this expectation, we know that expectation with respect to the some discrete value is the probability, because the probability is equal for all of them, it gets out of the summation, and the summation over all t. What happened? This is exactly similar to what we derived before. The summation is exactly what we derived before. So I can rewrite this L hat, this expectation of that term, as this value. So instead of maximizing R, I can minimize L hat. They are exactly similar. So we can minimize L hat instead of maximizing R hat. And this is the last slide. You do everything for x0 for one of the training sample. How we extend to the whole data set? Expectation with respect to the x0, the last part. So I apply one level of expectation over all data samples, and then everything is what we have before. This is exactly the extension we have in BAE. How from one data samples go to the complete data set. This is exactly similar to that part, nothing more. And this is the last objective function of the fusion models. As you can see, how do you start your training? You know how is generation. The training is start as follows. Sample one data from true data distribution,